How can the bad guys recover the passwords if they've been obfuscated through a cryptographic hash function that is impossible to invert? Imagine I'm attacking a system which hashes its passwords. So there's a hash function h from a domain P of passwords to a codomain D of digests. So hash of a password small p gives me a digest small d, and this hash function is computationally infeasible to invert. So once I have d, I can't recover where the password came from. And these digests are long, like 64 bits, 128 bits, 256 bits, and so this space is uniformly distributed over the very large space. And this password space, well, in theory the password can be any string. In practice, the password is not going to be of infinite length, so it's going to be a short string, and a short string that's fewer than 2 to the 128 short strings for some definition of short, and there's many fewer than that if you consider the password that people actually use when they log in, which are typically things that they can pronounce, they can remember, and so on. If I look at how many words there are in the English dictionary, that's of the order of 100,000, which is a very small number compared to even just how many strings of 7 characters there are. The space of plausible passwords is rather small. The space of all possible digests is very big. This hash function sends a password onto a digest in some unpredictable way that is computationally infeasible to invert. But still, even so, there is a theoretical possibility that 2 passwords might hash to the same digest. It's very unlikely, but it could happen, and this would be called a collision of the hash function. If I'm an attacker, I work on the assumption that I can probably penetrate that system and exfiltrate the file of credentials. Or if I cannot do it myself, I can probably buy it off someone else who's done it, or buy it on the dark web and so on, for some system. So from the file of credentials, which would be the hashes of the passwords of the users of the system, how do I recover their passwords so that I can then sneakily log in without leaving a trace? Well, if this space of passwords is relatively small, such as all the words in the English language or in any language in the world, that will there's only, I don't know, a few hundred languages in the world, so it doesn't increase the size of this this set by very much. I can even throw in all possible variations, such as, you know, the leet speak, where people substitute the letter E with the number 3, or the letter O with the number 0, I with 1, and so on. All kinds of variations and misspelling and so on. I can throw them in. Just going to be at most 2 or 3 other orders of magnitude over that. Is still a very manageable size for my password set. So I can explore all of this. I can try all the plausible passwords. That's called a dictionary attack, because I have a dictionary in an extended sense, and I try all the entries in the dictionary, and I see which ones match the digests of the credentials file that I captured, that I exfiltrated, or that I bought. Okay. As a bad guy, I'm a smart bad guy, and so I realize I can do all this hashing of possible passwords ahead of time, before I even get the credentials file. Regardless of which server's credential file I get, I can do all this hashing on my own in my spare time, and I can pre-compute a table of all the hashes of all the possible passwords in P. In fact, I can even trade it with my friends, because if they get hold of the credentials file of another server, they can use the same lookup table if the systems use the same hash function. And so great, we build this nice lookup table. We start from a password and we generate the digest by hashing it, but it's going to be keyed by the digest. So the key of our table is going to be a digest, and the value is going to be the corresponding password. It's going to be another digest and another password for some table that covers all the passwords in our set P that we are considering. So we like this approach very much as attackers, and we become more ambitious and we say, okay, well, we can afford a bigger table than that. Why don't we try just all the possible passwords, letters and numbers and uppercase and lowercase and symbols and so on, up to some length, okay? Length, 6 characters, it's very easy, 7 characters, 8 characters, get more ambitious, 9 characters, 10 characters. I can still do that so long as I can fit them in the table. Now, for each one of these possible passwords, I should also compute one hash. But this computation is very easily parallelizable because there's no dependency between the hash of one password and the hash of another password. So I can split that task into as many pieces as I want. I can give it to my friends. I can give it to people I don't know on the internet. Okay, you do this chunk, and then we put them all together. So massively parallelizable. I can expand this coverage of P to greater and greater P's. That's great for me as an attacker, evil mastermind. At some point, however, this lookup table, which given a digest tells me the password that is its pre-image, is going to be bigger than the biggest hard disk I can buy. Even if I am able to farm out the computation to other people and so do all the computation that's necessary to compute the table, I don't have space to store the table. Okay, so what does an ingenious bad guy do at that point? Well, you may have heard of rainbow tables. Rainbow tables are a construction to address this issue, but most people who talk about rainbow table, they don't really know what they're talking about, and they use rainbow table, they use this fancy name to indicate something else. Some people even call this lookup table here a rainbow table, which it clearly isn't. A rainbow table is a mechanism for the bad guy to be able to rely on a much bigger table than could possibly be stored in the biggest hard disk. A rainbow table uses a space-time trade-off. Now, the core of space-time trade-off is based on precomputed hash chains, and that's something that predates the rainbow table. It's simpler than the rainbow table. It's the core idea. We're going to work on the core idea first. Rainbow tables are an extra complication that, as I said, most people don't understand. So the space-time trade-off of the precomputed hash chains is that instead of being able to do a lookup instantaneously like this, get a digest, find which password it came from, or say that there's no such password among the ones in the P that I considered, because all these passwords are in this table, and there are digests, and I can, because this is a lookup table, I can, in constant time, tell whether a certain digest is in there or not, and if it is there, find what the pre-image is. Well, what I will do instead is I will do something where the lookup will take some time, not instantaneous, but in exchange the table is going to be small. I said precomputed hash chains. How would you make a chain of hashes? Well, the hash goes from a password to a digest, and the digest is a kind of different beast from the password. So what I really need is something that sends me from a password to digest is the hash, and something that from a digest sends me back to some password. And I'm going to call this a reduction function, which has the complementary signature from the digests. It sends me into the passwords. Now I said the cardinality of this D is typically much bigger than that of P. So clearly this reduction function is going to have collisions for sure, because there's going to be many billions of digests that map to the same password, just for pigeonhole principle. In here, the hash function, because of the way it's constructed, it's all random stuff, there's no guarantee that passwords will never collide. But it's pretty unlikely. Whereas here, it's pretty likely that several digests will map to the same password. But on the other hand, there are so many digests that I'm unlikely to pick digests that map to the same password. Anyway, I am slightly digressing, but we will revisit this a little later. But the fact that this is much more populous than this other set is the reason why we call it a reduction, because I reduce it to a smaller set here. So the chain works like this. I start from something that might be a password, and then I apply the hash, and this takes me to a digest, and then I apply a reduction, and this takes me to another password, and then I apply hash, and this takes me to a digest, and then I reduction, and this takes me to a password, and apply the hash, and this takes me to a digest. Now I'm using the same letter here, P. It's not the same password here, it's different password. It's not the same digest here, it's different digests. As I said, clearly the reduction function is not the inverse of the hash function, because the hash function is by definition not invertible. It's just something that takes a digest and returns a password. It scrambles things up. It's going to be some password that has no rhyme or reason, but basically I'm throwing it back into a space of password so I can apply the hash again, and then I can apply the reduction, and then I can apply the hash, and I can make a long chain here. So here I start from a password with 2 hops, hash and reduction. I go back to another password, 2 hops, another password. I can make a chain that contains a certain number of passwords, let's say L passwords, length L, and I will have about 2L hops. The interesting thing here is that I can, from the start, I can reconstruct the whole chain. It will take me the time of doing 2L applications of this function, L applications of the hash and L applications of the reduction. I can reconstruct the whole chain if I know the initial value, so I will use this fact to save space by throwing away most of the chain and only remembering where it starts and where it ends. And I'm going to key things by the endpoint, and the value matching the endpoint is going to be the starting point. So I'm going to have something that looks similar to this, but this digest here is going to be the digest at the end of a long chain, at the end of a chain like this of containing L passwords, and the P is going to be the initial password here. So each one of these entries, instead of being worth 1 password, is going to be worth L passwords. And assuming that these things never overlap, then I can basically cut down by L the number of entries that I need to store in my table in order to cover all of P. And so if I make very long chains, then let's say 1,000 or let's say 1,000,000 or whatever, then I divide the space used to cover all of P by 1,000 or 1,000,000 or by L or whatever is appropriate. And the price I have to pay for that is that to actually span all these passwords, I have to reconstruct the relevant chains. Now, fortunately, I can do that by reconstructing just the chain that I need. I don't have to reconstruct all the chains, which would be quite expensive. And how do I do that? Let's say that I want to find the preimage of a given digest D. I'm given D, I found it in the credentials file, and I want to know which password, when hashed, gives me D. And I first look in here, is D one of the keys of my table? If it is, then obviously it's the final value on a chain. And I can just reconstruct that chain and look at the last hop, and the last hop starts on the password whose preimage is D. Great. What if D is not one of the end values? Well, maybe it was one of the things that I threw away in the middle of some chain. How can I find out which chain? How can I find out which chain? Well, I take D, and because it's a digest, I reduce it and I get the password, and then I hash that and I get the digest, and I reduce it and I get the password. And as I do that, every time I hash an intermediate password, I check if the digest that results is one of these keys, which I can do in constant time because this is a lookup table. So is this digest one of the keys? If it is, then I have identified a chain that I could reconstruct from the start, and then I would find, by starting from the beginning, the password that eventually hashes to the digest I was given. If I don't find any of the final digests after having repeated this process 2L times, so after having generated P passwords, then I know that because all the chains were of length P passwords, then I have basically not encountered my sought digest in any of the chains that ended up in those values here, and so this digest was not stored in my table, because remember, this table here is made so as to cover all of this. It's never made to cover all of that, which is too big to even compute, never mind store. So in summary, constructing these long chains and throwing away most of the chain and keeping just the beginning and end in this table, that's the endpoint, which is the key to retrieve the starting point, allows me to cut down the space necessary for the lookup table by a factor of L, where L is the length of the chain in number of passwords it stores. And so that's how I compress this big lookup table, and I'm able to explore bigger and bigger versions of P with something that still fits in my hard disk. And I said I must do enough chains and long enough chains that with all the passwords that they visit, they cover all of P. If I am so lucky that each of these chains visits different passwords, then to cover all of P, I just need P divided by L chains, where L is the length of one chain. And that's nice. Now all this was under the somewhat naive assumption that there are never any collisions. But as we said, as we make the chains longer, the probability of collision goes up. And let's have another chain here. So these chains start from different passwords, end up in different digests. So now imagine that because of a collision in the reduction function, this digest is different from this digest. Okay, different. But this password is the same as this password. Equals. Okay, that's because of a collision in this reduction function. Two different source digests result in the same destination password. Okay, so then from then on, hashing this password gives this digest, which is going to be the same as this digest. So all of this is going to be the same as this, this same as this same as this. From the collision point onwards, these chains are going to be the same, of course. So let's now give some names to the digest. So let's imagine the situation where I am looking for the preimage of digest G. What is that? What I do to find out the preimage of digest G, if I'm given this table of precomputed hash chains, is I have to reduce and hash this dg up to 2L times and check at every step if the digest I get is in one of these keys. Is dg one of these endpoints? No, it's not. Okay, so then I'm going to reduce it, which takes me to this password here, and then I hash it again, and it takes me to the h. Is the h any of the end values? No. Then I reduce it, and it takes me here, and then I hash it, and it takes me to here. Is it one of these end values? No. Then I reduce it, and I hash it, and it takes me to the e. Actually, the e is here, is an end value. So there's going to be, one of these entries is going to be the e, and it's going to start at this password. Let's call it password, I don't know, A. Okay, so I'm going to call this one password G. So it's going to be an entry here, DE password A, and there's going to be another entry, DF password G. So this chain is this entry, and this chain is this other entry. So by reducing and hashing this one, I end up actually here, DE, and it says, okay, now you should explore this chain that starts at PA. So I rebuild this chain, and at every step, the A is this, the digest I was looking for, DG. No, it's not. Is this DB the one I was looking for? No, it's not. Then reduce and hash. Is it this one? No, it's not. Reduce and hash. This one? No, it's not. Reduce and hash. This one is not. I run through the whole chain, and I couldn't find my digest. Why is that? Because the digest came here because of a collision, and actually I should be looking at another chain, this chain, and so I have to say, that was a false alarm, sorry, even though I ended up here, it's not in this chain. So I should continue this until I get to 2L, because continuing here would actually be continuing here, and then I may now find this one, which gives me another chain, and then if I restart from this chain, I will actually find my DG over here. I may find something that is a key in my table, and I follow that chain and it didn't work. In that case, it was a false alarm. In that case, I have to continue the chain that I stopped at, in case it was part of some other chain, and again, until I get to 2L. If I get to 2L and I still haven't found the preimage of my value, then it means that that digest does not have a preimage in my table. But I may have one or possibly even more than one false alarms on the way to that. Now you can see that these collisions have another annoying property besides that of slowing down the retrieval of my preimage, and it is that from here onwards, from the collision onwards, these two chains contribute the same passwords, and so my naive assumption that I could, if I didn't have any collisions, I could exhaust the space of P with chains of length L by using only P divided by L entries over here in this table, that no longer holds, because here these two chains don't contribute L passwords each. They only contribute distinct passwords up to the collision point, and from then on they merge and they only contribute the passwords of the longer one, and this one is absorbed into this one. So this is waste, and the more collisions I have, the more waste I have, and this means I must compensate by having more entries in this table than I would otherwise. And I can even have a collision between a chain and itself, in which case I end up having a cycle, and then anything from the collision onwards is just revisiting the passwords in the cycle, and I don't contribute any further passwords. The earlier the cycle occurs, and the more wastage there is in the things that would have happened after the cycle. This is a problem of the precomputed hash chains, which is more significant the longer the hash chains become, and so this puts a practical limit on the length of the chain. The precomputed hash chains were introduced in 1980 by Martin Hellman of Diffie-Hellman fame, one of the inventors of public key cryptography and winner of the Turing Award. And in that 1980 paper, he developed the maths of the probability of getting collisions as a function of the length of the chain and so on. And he even suggested an improvement, which was to say, if you go beyond a certain length of chain, instead of doing that, keep the chain shorter and use different tables. Start a new table with a different reduction function. If you start a different table with a different reduction function, let's say that this collision happens between the chain in one table and the chain in another table, then you can still have a collision between this digest reducing to this under the first function, and this digest reducing to that under another function, but from here onwards the hash is going to be the same, but the reduction here is going to be different than the reduction here, and so this is not going to continue colliding, and so this saves the day in some way. But it forces you to have multiple tables, each with its own reduction function. Now, a bit over 20 years later, in 2003, at Crypto 2003, Philip Oechslin introduced a variation on the precomputed hash chains called the rainbow table. That's what the rainbow table actually is, where you have only one table, but within the table, every reduction in the chain is done with a different function. And so if you have a collision between different chains, then the rest of the sequence after the collision is not going to be identical between the two chains, except in the very unlucky case that the collision happened at exactly the same step in both chains. In this example, the collision happens at different stages in the two chains, so the reduction that leads to the collision is here. The hash is going to be the same. The reduction after that, with this same input for this function and this function, because this function is different from this function, then these two passwords are going to be different, and so we do not continue with identical sequences after that. Only in the case that this happens to reduce to the same as this in the same step, then the sequences are going to be the same here. And there's of course a more elaborate procedure for checking whether a digest is in the table and which chain it is, because you have to take into account the fact that the reduction function is different at every step, and so you have to guess which step your digest might be at by trying the various positions that it could be in, and so this makes for a somewhat longer lookup but a more efficient table, and overall there is a gain compared to the precomputed hash chains. The precomputed hash chains no longer work well when there are collisions, which are inevitable when the chains become too long, and so various optimizations have been introduced, and the best of these is the rainbow table. But interestingly, even before the precomputed hash chains had been introduced, a countermeasure against the lookup table had been devised in the form of salting by Unix security architects Robert Morris and Ken Thompson. Salting passwords means instead of just hashing the password itself, I concatenate a random string to the password and I hash this concatenation. Now, in the salted passwords Unix scheme devised by Morris and Thompson, I don't keep the random salt secret. I store it. Let's make a distinction. This is the attacker's lookup table. Either the uncompressed one if it's direct lookup, or the compressed one if this is just a beginning and end of a chain. Now, I'm going to make another table, but that's the table of credentials that is stored on the server, and that's the one that the bad guy wants to steal and that the good guy imagines might be stolen, and so doesn't want to store plain text passwords in. So I don't store passwords in there. What I store is I store digests. One digest per account, but in this case I will also store a salt next to the digest. So salt, another salt, another salt, another salt. And here each of these lines is associated with a particular user. So I have user ID here, user ID, user ID, user ID. So if a certain user wants to log in, that user will supply a password, will supply their user ID and the password. So I look in the line of their user ID, I get this password, I concatenate it with the salt, I hash the concatenation of supplied password and stored salt, and I check if the result of the hash gives me the digest that's in this line. If yes, then this user is logged in, and if not, then this fails. Now, clearly someone who exfiltrates the credentials file can see the salts. The salts are available to the attacker. So the attacker can do exactly the same check. Is this password valid? Well, I just concatenate with the salt and I see if it gives me this digest. But because all these salts are different, what the attacker cannot do is the precomputation of a lookup table, because they would have to have as many variants of the lookup table as there are different salts. So in the original Unix Morris-Thompson scheme, there were 12 bits of salt, and so 2 to the 12 variations of this, which means 2 to the 12, which means 4,000 different lookup tables, increased by 4,000 the space that an attacker would need to devote to making these lookup tables. By today's standards, this is not very much, and it's something that could be compensated by making the chains 4,000 times longer. But nowadays, we make salt something like 128 bits, and so you'd have to have 2 to the 128 times more lookup tables, which of course is infeasible there. It doesn't exist enough atoms to store all these bits. And so this completely defeats, this scheme of salting completely defeats the precomputed lookup table attack. Whether the lookup table is compressed by using precomputed hash chains or even rainbow tables is completely immaterial. A salt of sufficient length will totally defeat any lookup table type of attack, whether the lookup table is compressed or not. But interestingly, Microsoft, in their wisdom, continued to use unsalted hashes well after Morris and Thompson introduced salt, and in fact, indeed, throughout the 2010s, For backwards compatibility, systems deployed by Microsoft in hundreds of millions of instances called LAN Manager and NT LAN Manager still accepted a scheme of unsalted hashed passwords. And this is why rainbow tables were weaponized and used and built up to considerably large sizes, and there existed rainbow tables that could crack all LAN Manager and NT LAN Manager passwords with certain rules up to a certain length of the password. And a distributed effort was set up for farming out the computation of these rainbow tables for larger and larger sets of P, which resulted in a website called freerainbowtables.com, which could produce any NT LAN Manager password that had not been created by a security geek. So what has made rainbow tables obsolete is essentially the demise of NT LAN Manager. But there's no end to human stupidity, and there are still plenty of systems that are based on homebrew versions of login procedures that don't hash the passwords or somehow store the credential in a form from which the plaintext version of the password can be recovered, which is a pretty dumb thing to do. And there's a wonderful website called plaintextoffenders.com that names and shames the websites that do that and store the credentials in a form from which the plaintext can be recovered. And they have some pretty sensible advice on what someone who runs a website with a login function should and should not do, and it's worth having a read of that.